Okay, by request, I'm going to do a little video on the ideal gas equation. Now, the ideal gas equation concerns the gas environment, and there are certain parameters to a gas environment. There's the pressure that the gas is exerting on a container. There's the volume of the gas. There's the number of molecules of gas, which is always measured in moles. There's the ideal gas constant, and then there's the temperature of the gas. So here's one form of that formula, and here's the other. Now, I've circled R because R is in units of entropy, and the number for R depends on the units chosen for each of these variables here: pressure, volume, temperature, and moles. If you decide to find different number rather than moles, then that will affect the number for R. Okay, so in the ideal gas equation, from the ideal gas equation, we can derive all the gas laws, all the other gas laws. There's Boyle's law, Charles' law, Guy de Sac, and Avogadro's law, and the combined gas law. And this little symbol here, that's the ancient symbol for equals. Right now we have the equal sign, and that looks like this. Used to be equals look like that. Now we use this to say is proportionate to. The volume is proportionate to temperature. Pressure is proportionate to temperature. Pressure, volume are proportionate. Pressure, volume per temperature is proportionate. Okay. So we can come up with a whole lot of different numbers for R based on choice of units for these different things: pressure, volume, even temperature. Temperature has to be absolute temperature, and we generally have two choices for that: the Kelvin temperature scale or the Rankine. Rankine scale corresponds to the Fahrenheit temperature scale, and the Kelvin scale corresponds to the centigrade or Celsius scale. We used to refer to it as degrees Kelvin, but anymore for some time now, for some years now, we just call it kelvins. Okay, so the actual physical dimensions for the gas constant is actually physically dimensionless. It's in units of entropy, that is energy per temperature, usually joules per Kelvin, the typical units. But temperature in physical units is the same as the physical units for energy, so they cancel out, and we're left with what is physically dimensionless units of entropy, which of course makes sense, doesn't it? Okay, so we say that pressure and volume vary inversely, right? If we have an equation where P times V, right? As pressure goes up, volume goes down, all things considered equal. Likewise, if volume goes up, pressure goes down, all the things kept equal. So it varies inversely. Now, volume and temperature vary directly. All things else being equal, volume goes up, temperature goes up, so does volume. Same with pressure. Temperature goes up, so does pressure. And if we put in more, say we put in more molecules, then that tends to up pressure and volume. Okay.